Hello and welcome to Chapter 10 video, and the purpose of this video is to discuss something called analysis of variance, or essentially it's a comparison between two means or three means of a group. Notice in front of you the slide I have some sort of descriptions, if you will, of ANOVA, because if you're like me, when I heard the term ANOVA and I saw essentially this bit right here, I was just like freaked out. But basically, all ANOVA is what this is. It explains it right here. It's a comparison between various different groups where we're looking to see if their means, so like here in this picture, if their means are enough apart for us to say that this group is actually different from this group, which is actually different from this group. Up until this point, we have just used estimation and hypothesis testing to analyze a population mean. But in this chapter, we're going to be able to actually extend our analysis to do a comparison of 2 or 3 different means. So that's an important step, because up until now, we really have spent a lot of time focused on describing our data, thinking about, what exactly is our data telling us? Is it normal? Is it properly distributed? But we did all of that because we want to use some of these tools like analysis of variance, ANOVA. We want to be able to compare a group to another group to say, hey, this group is actually different from this other group. We do ANOVA very similar to the other stuff we've done. It's a lot like the z-test calculations. It just has a little bit, some different twists. Sometimes we're going to use a t-table instead of the z-chart, and sometimes we'll use an f distribution instead of a t-chart or a z-chart. But basically it's all sort of the same idea. Is the difference between the two groups sufficient enough for us to say that yes, there is a statistical difference between this group and that group? So what I'm going to do is take you through a series of examples, and I'm going to show you some different formulas, but I want you to keep in the back of your mind that this is all very, very, very similar to the same formula we've been using all along. Basically this formula right here. It is different. Whoops, this thing is missing off of my, there we go. It is different computations. They're a little bit more elaborate, but the basic idea is the same. We're trying to look and see if this mean here in the blue group right here, if it varies enough that we can say it's actually different than, say, the pink group or the green group over here. And we do that by looking plus or minus 3 standard deviations on either side to see if those means overlap. Like I said, the computations are a little bit more complicated, but basically it's the same idea. So I'm going to take you through it, and hopefully it'll be all right. And you'll see in the end that even though this stuff right here sort of looks complicated, really, it's okay. It's not all that different from the other stuff we've done. So the first thing that we want to talk about is the notation and that goes along with some of the equations and that sort of thing that we're going to talk about. So in order to make inferences about the difference between two population means, we have to have, first of all, independent sampling for this part of it. So we need 2 random samples that are considered completely independent. When we have the complete independence, this generates a sample that we can use that's separate from the other sample. So we want to make sure that we've got the 2 separate samples, and we're going to call them mu1 and mu2. So basically that's all. So we want to do a test that's going to show that mu1 is equal to mu2 or not equal to, or whatever the case may be. We call this difference a confidence interval between mu1 and mu2, and the way you will normally see it written is mu1 minus mu2 is equal to 0, or mu1 minus mu2 is not equal to 0. Because if you think about mu1 minus mu2, if mu1 is equal to mu2, then of course they're going to equal 0. If there's a difference, well then it will not equal 0, and so we will not be able to reject or accept the hypothesis stating that mu1 is equal to mu2. Now, remember that x bar 1 minus x bar 2 is the point estimator that we use for mu1 minus mu2, and that's because we're using samples. We're never going to have, the entire population of mu1 or mu2. So we use this, x bar 1 minus x bar 2, just like we have always, to sort of signify the fact that we have this sample. We of course have to make the assumption that the samples are independent and they are normally distributed. And so we do that by noting that n needs to be greater than 30, and they have to, be independent in order for the central limit theorem to work. And actually, before I go on, I'm going to pause here for a second. I just want to make a note about your problem, your assignments. So in this case, all the stuff you're going to do in the textbook, they're going to tell you, oh, this is normal, or the n is greater than 30, or whatever. But remember that in your assignments, you have to make sure you show that this is definitely the case right here, so that it's normally distributed and it fulfills the central limit theorem because we've got an n greater than 30. And so remember all my emphasis about the multiple years of data. Well, in order to do the ANOVA, which is certainly one way to test a hypothesis, you got to have a large n. So, I mean, just as an aside, it doesn't really impact you on the homework problems, but definitely impacts you when you get into your own assignment and, what your interests are. So in front of you, what you have is a little excerpt out of the text. At the very beginning, they talk about a situation where stores having greater than 20 companies in their chain or something like that have to post caloric in the calories of the items that they offer. So they have this little example in the textbook: drink calories and food calories. And in this case, we've got the before and the after that we're going to compare. And so this is the introduction case, and it sort of pulls together several different pieces of what we're talking about. So I thought it was kind of a nice example. So they get it from, whatever people's credit cards, and so I just went in the textbook and I pulled the data off, and I have on the next slide, a picture of all the data and then the sampling, the tests that I had to run, etc. So let me just show you that. So actually, I decided to show it to you in Excel because then I could show you how to do the test. So here we've got the drink calories and the food calories, sort of before and after. So this is actually two separate data sets, but I just put them all on one page here just so I could show you. So we're going to start out with doing the food calories, this yellow column, because this one actually turns out to be different, so I thought that would be a better way to do it here. Alright, so what I'm going to do is I'm going to go up here to data and to data analysis, and I'm going to choose, in this case, t-test. Let me hide this, gets out of the way. In this case, I've got a t-test, which is a paired. In this case, we've got a t-test with paired sampling because we've got before and after. So we're going to hit OK. And then we're going to highlight the variable in the first range. So we're going to click on this first one, do Control Shift and the down key, and that's going to take us down. Now I had already put the average standard deviation down there, so we don't want to include that. So I just undid that. And then also I've got this one, Control Shift down arrow, and then Shift to hold it to bring it back up to there. Now I want the hypothesized mean difference to be 0. I have no labels in this because I didn't highlight before and after. I've got my alpha set at 0.05 because that's the way the problem is set up. And then I want my output range to be maybe right here. And I'm going to say OK. And I'm going to fix this up so I can read it. So I was going to just fix it up and leave it there, but then I decided that, and I would just sort of show you the difference. So here is the way that it gets produced by Excel, and then here is where I just kind of cleaned it up so I could read it. I don't know about you, but I just find this difficult to read, and it doesn't make near as much sense to me. So I changed the decimals and I highlighted a few things, and just makes more sense to me. So I'm gonna delete this because it's the same, it's just that this one is easier to read. So I'm just gonna say delete and shift shells up, and there we go. So this is essentially the output. Basically what it tells us is that the mean and the before and the after mean, which is the same really as what I have calculated down here. I mean, there's really no difference. And the variance, and I have the standard deviation, so it's really just the square root of these two numbers here. And we have 40 observations in each, and it gives us these other things, our hypothesized mean difference, which we say should be 0. Make that a little bigger there. And then degrees of freedom, which is simply the n minus the number of things we're looking for. In this case it's 1, so it's 40 minus 1. And then we have this t-stat. So the t-stat I have next to it is there's plenty of difference. So the way I think about the t-stat is it's sort of like the z-value when you calculate, when you do the z-test. It isn't exactly the same. So for those of you who like exact interpretations, you may not like this interpretation. But basically what this tells us is there's quite a bit of difference between these two means if we consider the error associated with the means. So in the textbook they use a great terminology for this, I think, and that is that we've got a point estimate, and the point estimate is essentially the difference between the means. So let's just write that down here. So we've got the point estimate, which is the difference between 400.275 minus 391.475, and we get this a 0.8, and I had already calculated it in Excel before I put it into my trusty little iPad here. So we know that the difference between the two means, just the differences between the means, is 8.80. So we know that the hypothesized difference between the two groups is about 8.8, and so we have that reflected right here. I switched over here to my iPad so I could sort of talk you through this. And then now we need to talk about the error. Remember I was telling you before we had the point estimator plus or minus the margin of error, and the margin of error essentially is the standard deviation. Problem with the standard deviation now, because we've got two groups, is we don't just take the standard deviation, because which one would we use, right? We've got two groups. So in the case of a matched pair set, computing that standard deviation, is a little bit more involved. So for right now I just want to stick with the output of the Excel. So let's just take a look at the output, and we see that we have the means and we have the variance, just like I said before, and then down here we get to the t-statistic. So the t-statistic is what we're looking for. That is essentially the z-value for all intents and purposes, if you want to think about it that way. There's about 6.7 standard deviations between the two means of our groups, thus they don't overlap, essentially, if you want to think about it like that. The standard error between the two, one way you could do it is to just take the pooled error, and if you were to take the pooled error, you end up with about 1.51, and I'll get into how to calculate the pooled error in a few minutes, but for now I just want to tell you it's about 1.51. And then if we use the pooled error and we divided that into our 8.8, well, then we find out that we have a difference of about, sorry, I had to find my paper, so a difference of about 5.8. So that isn't the same as 6.7, I understand that, but it gets us pretty close. So basically what this says is that there is indeed a difference between the calories that are consumed before and after the calories were posted on the menus. And in this case, we can say that these two groups are actually different. There is no, we can reject the null being that mu1 is equal to mu2. We can say, no, mu1 is not equal to mu2. And we can tell that because our t-stat is so large. It just needed to be 1.6, and it's actually 6.7. So we can definitely reject it. So now, with all of that as a background, I'm going to take you through an example from the textbook. So first things first, there are two ways to examine the point estimator plus the margin of error, and the first way is denoted here with this z value as a part of it. So here we're going to take the difference between the two means, and then we're going to add to it the margin of error, and the margin of error is computed this way when we know the variances of each group, and we want to create a confidence interval between mu1 and mu2. So this would be the model we would use. Now the second model that we would use is when the variances are unknown but we assume they're equal. And in that case, we need to use this t calculation. This is basically the same, a little bit different, but we have to use a student's t distribution as opposed to a z distribution. So the example I'm going to actually do here is going to use this model here, and it's quite similar to the one with the food and the drink that we were just talking about, but a little bit different. So we'll go ahead and get started on that example, and I hope this makes some sense to you. All right, so in this case, we have two brands of cigarettes, and we are assuming that the differences in the variances are known, but we aren't entirely certain, so we're going to use a t-test for this. So here's our brand A and our brand B, and this is our x1 and x2, and you can see that there is indeed a difference between the two, but we want to construct this 95% confidence interval that they are actually different. So we do this by setting up this equation right here, where we're going to take 20 minus 1, because that is, let me just start by saying, the calculation in front of you is how we calculate the pooled difference. So remember I told you earlier that one of the complex parts about all of this is we can't just use the standard deviation of one sample or the other. We have to somehow come up with sort of a pooled standard deviation, if you will. And so we start by calculating the pooled variances. So in the case in front of you here, what you've got is, just basically n minus 1 times 0.22, which is the variance for group 1, plus the n for the second group minus 1 times the variance for the second group, both of those squared. I'm not sure if I said that before. Then we're going to divide that by n plus n minus 2. So that gives us our degrees of freedom. So we end up with 43 degrees of freedom. We divide that into that numerator, and we should come up with 0.0535. And essentially what this gives us is the pooled estimate to go with our difference that we're going to compute. So what we want to do here is, this sort of jumps, I think, a step, so I want to write it out for you. We're calculating the difference between mu1 and mu2 here, and so if you remember from the previous slide, we've got 1.68 is the amount of nicotine in the cigarettes in group 1, and then we want to subtract from that 1.95. And that difference turns out to be right here, this negative 0.27. Now this value right here is the t-stat that we're interested in. Remember, we're using a t-test here. And that t-test is calculated as t, and we want to take alpha divided by 2, and we want also our degrees of freedom. So we've got t, our alpha divided by 2 then is 0.025, and then our degrees of freedom, like I said on the previous slide, was 43. So now what we're going to do is look on the t-table, which is at the end of your textbook and one of the appendices, but I have it inserted here, so I'm going to go to this next page so you can see it. And what we do is we come down this column over here on the left. This is the degrees of freedom column, and we look for our number. So we don't see 43 there, so we got to go over to the next page. So we come straight down and we find 43. Then we have to find the right alpha at the top. So in our case, we wanted our alpha was 0.05, but because it's two-tailed, because it's an equal sign, we had to divide that by 2, so we got 0.025. So we come across until we get to right here, I believe is the right number, yep. So because we've got 0.025 as our alpha that we're interested in, and we had 43 degrees of freedom. So we bring this number 2.0017 back over here, and you see I've got it here. So we've got the point estimator is here. This is our point estimator, plus or minus our t value times this right here, which is our, essentially it is the margin of error that we're interested in. So we multiply all that out, and we find out that we've got 0.27 plus or minus 0.14, or our difference ranges between 0.41 and negative 0.41 and negative 0.13. So what that tells us is that our difference does not cross over 0. So that means that we cannot, what that means is the the original hypothesis that mu1 is equal to mu2, that's the null. We are going to reject the null because we know that mu1 does not actually equal mu2. In fact, they are different. They don't include 0. So we had our HO, which is mu1 equal mu2, and HA, which is mu1 not equal to mu2. So we're going to reject the null in favor of the alternative, because in this case our analysis suggests that 0 is not included in our t-test. So therefore we can feel pretty confident in rejecting the null hypothesis in favor of the alternative. Okay, with that, I want to stop this video and tell you that you should do these problems 15, 16, and 17, all of which have data, because I just think it's a little easier to do it with data. I will create a separate video over the refrigerator longevity, that's problem 15, and explain that one. But I wanted to get this video completed and then leave the problem 15 one separate. So I hope this is helpful. I hope it's making sense to you. I'm trying really hard to simplify it, but it's complex, so it can sometimes be challenging to make it simple. All right, have a great day. Bye.